Hi everyone, my name is Daniel, and today I'm going to talk about a massive southern ocean phytoplankton bloom fed by iron of possible hydrothermal origin. Okay, so let's first take a look at the basic knowledge I think you have to know and my research motivations. So first, how does dissolved iron impact the ocean? So we all know that phosphorus, silicon, and nitrate are the basic nutrients in the ocean to supply phytoplankton to grow, right? So besides them, there are still some trace elements such like dissolved iron that is important for phytoplankton to grow too. So without dissolved iron, the phytoplankton just can't grow well. And then let's take a look at the environmental conditions of the Southern Ocean. So the seawater in the Southern Ocean is basically, especially in the polar region, there are high nutrients and low pH. And what make the result of the high nutrient and but low pH is because in the region of Southern Ocean there are lack of the iron. So even though the nutrient is very high, but without iron, the phytoplankton just can't grow well, and then it comes the result of low pH. But recently we find a bloom on Southern Ocean that almost appears every year. And this is what made us very curious. And then let's take a look at the geographical location. So in this graph, you can see the center is the Antarctica, and this one is Australia. And this place is our research location, just between the Antarctica and Australia, like in this place. So let's look closer. So you can see the orange line and red line here. And there are the hydrothermal vents, which is KR2, KR1. And there are two white dashed lines here on the southern Antarctic circumpolar current front and the southern boundary of Antarctic circumpolar current here. So, and then let's take a look at this graph. And this one is the mean net primary productivity around this area. So I want to talk about what is net primary productivity, which is NPP. And so basically it's a rate of how much energy the primary producer provides to a consumer in that area, in that ecosystems. So you can see in this area, the NPP is way higher than all the other area. So we know that this place is where the blooms appears at. And so let's look closer, and this orange line and gray line are the bands, KR2 and KR1, and purple line and pink line are the SCCF, SPSCC, and all the white dash line, this one is the bathymetry and currents, and all the white dash line are the current flow. And at this graph, we can see the profile A concentration. So we can see at this part, the profile A concentration is very high, and which is where the bloom appears at. And all the numbers here are our sampling stations. So here's our guessing. Do the band supply something important to the bloom? And why does the bloom appear at there? Does the currents and the bathymetry play an important character too? So to answer our questions, we have to find out a way to find out the solution. So here's our methods. So we use the CDD during our cruise to our research location, and we use CDD to get some basic data such like temperature, pressure, dissolved oxygen, and we use the CDD to get our water sample and we can back to the lab and find out the concentration of diffusion iron. And then we use the aqua satellite image, and we use that to find out the distribution of purple A in our research region, and then we can find out where the bloom appears at. And then we use the laboratory plume modeling, and then we can find out the transmission of the particle in the seawaters. And in the lab, we use Argo as the background data. So here's our result. And this one is the concentration of profile A, and all the number on the graph is the station, and this one is depth. The y-axis is depth, and the color meaning is the concentration. And you can see between the 136 to 120 is this plate part, and you can see this part is the bloom place, and the profile A is very high here. And so does the PLC, but the PLC is very high is because that the bloom appears here, and it means there are a lot of organisms here, and so the PLC is very high there. And this one is nitrate, and we can see the nitrate concentration is very high, and this part is very low. And the reason why this appears is because that the phytoplankton, when the phytoplankton grow, they have to consume nitrate. So the nitrate getting used by the phytoplankton, so the concentration of nitrate here is very low. And the last one is the diffusion iron. And you can see the diffusion iron concentration on the upper of the ocean is very low, and the reason is just like the nitrate, they are consumed by the plankton. But there are something strange here. We can see that the diffusion iron here is very high, and it just below the place where the bloom appears at. So this is something we think is important. So let's compare these four graphs. We can see the bloom appears at this part, and the diffusion iron here is very high, just below the bloom part. So let's take a look at the diffusion iron supply. So at this graph, the y-axis is the depth, and the x-axis is the diffusion iron concentration. And you can see the gray line and the black line are the station out of the bloom, and the green line are the station inside of the bloom. So first, diffusion iron is high when the depth is deep with the station at. And then the diffusion iron start getting difference at this part. And finally, diffusion iron will get low when they are on the surface. So we want to know whether you can see the drum field here. So we want to know whether the drum field of diffusion iron is sufficiently supply the phytoplankton to grow. But before that, I want to mention you something. I want to talk about the concentration of diffusion iron transformed to the concentration of PLC. So we all know that when the phytoplankton grow, they have to consume iron, right? So when phytoplankton grow, the concentration of diffusion iron will get low. So first, diffusion iron getting absorbed by phytoplankton, and then the phytoplankton will die, and then the dying phytoplankton will become PLC. So the PLC concentration will get high. And we know that the different species have different ratio of transform diffusion iron to PLC. And then we can know that because we want to determine whether the diffusion iron is sufficiently supply the phytoplankton to grow. So we calculate the ratio of how the diffusion iron transforms to PLC accumulated range. So the station within the bloom, their diffusion iron transformed to PLC accumulated range is 4.0 to 5.2 mmol per mole, and then which is falls into the P Antarctica diffusion iron to PLC accumulated range. And P Antarctica is the dominant species inside the blooms. So we can know that the diffusion iron really supply the phytoplankton inside the bloom. And when the outside of the station outside of the bloom, the diffusion iron to PLC accumulated range is 13.0 to 1.2 mmol per mole, which is not falls into this one. So we can know that the diffusion iron really supply the phytoplankton inside the bloom. And back to the gassing, we know that the gas really supplies something important to the bloom, which is the diffusion iron. And then let's take a look at these two pictures. And we find that the gas is right here, but the bloom appears at this place. So, and we can know that current flow like this way. So we think it's the flow transmission or the diffusion iron to this place. Okay, and this is a graph of a water mass edge, and we find out anomalous water mass here. You can see their water mass edge is very young, and they are colder and fresher. So, as a laboratory modeling we use, we find out that we can see that this one is eddy connected energy, and this one is net primary production, and this one is a bathymetry, and you can see this y-axis is the depth. And first, when the intake current flow, and because of the bathymetry here, the ACC will become weaker, and you can see the eddy connected energy will get low. And then, because we all know that energy won't get disappear, right? So it becomes the upper volume water here, and the upper volume water will bring all the diffusion iron onto the surface, and then it comes to the bloom, so the net primary production is getting higher. So all of this data is from our research of the laboratory model. Okay, and let's get back to the guessing. So we know that the bathymetry and currents really play an important part, right? Okay, and here's our conclusion and future prospect. So we know that the bloom caused by the KL1 and KL2 hydrothermal vents because they provide the important diffusion iron. And then we know that the currents and bathymetry play an important character to push diffusion iron together, because without them, the diffusion iron can't get to the right place. And then, so the consistent location and productivity of the bloom has apparently made it a hotspot for upper trophic level activity. And furthermore, we find in other research, we find out whales visit the region of the bloom, suggesting well-established migration pathways and persistent use of this feeding ground. And although the Ross Sea Marine Protected Area covers a few small portion of the bloom region, just like this pink area, but the majority of this important foraging area remains unprotected. As you can see, in this graph is the global A, and there are still a lot of parts is unprotected. So, and the bloom is important to our upper trophic levels and is a potential CO2 sink, but the region of it decreasing rapidly, resulting of the climate change. So, this is my presentation, and thanks for listening.
I think he used a simple freehand words to explain a hard concept, led me to easy to comprehend. But the talk speed and the content of the slides is a little bit more. You have much content in this one slide.
I think the data you talk is detailed, and you have some movie image to explore the context. You speak a little bit faster to me, but because you have many content, so I can still accept it.
Every part is explained clearly and also has a good connection in each part. And although it is over time a little bit, but your logic is clear, so I think many persons are not very distracted.
Okay, thank you.